Hi there, this is Dr. C. Sonia, Assistant Professor in Chemistry, SNS College of Technology. In this video, we are going to see how to determine the hardness of water using EDTA method. In this, we are going to learn and practice the quantitative techniques for determining the concentration of solutions. We have to consider the safety consideration like the pH 10 buffer solution should be kept in the hood. We have to avoid the breathing ammonium vapors from the buffer. Eriochrome black tea will stain the skin and the clothes, so it should be kept away from them. And all waste materials can be safely rinsed down the sink. We are going to see the apparatus that is used in this experiment. You have the pipette with the elongated tip, measuring jar, standard flask, wash bottles, contain the deionized water, then pipette bulb, beaker, conical flask, viewed with a stand and the porcelain tile. So EDTA has a greater affinity for the calcium and the magnesium ions when it is in the form of dihydrogen anion. This is the ionic form of EDTA at the pH 10. So determination with the EDTA, the hardness of water is said to be hard when it contains calcium and magnesium ion. These ion reacts with the soap to form an insoluble substance called soap scum. So the calcium and the magnesium ion along with the other metal ions such as iron and lead can be removed from the hard water by the addition of EDTA. So we'll see what's the principle involved in this. That is, the principle of EDTA titration is based on its ability to chelate or form stable complexes with the metal ions, particularly divalent metal ions such as calcium and the magnesium ions. So EDTA is an hexadentate ligand. That means it can form 6 bonds with the metal ion. This property is utilized to determine the concentration of metal ions in a solution. So the sample collection, that is a water sample, is collected and it may contain various metal ions, especially calcium and magnesium ions, which contributes to the water hardness. So the complex formation is the collected water sample is treated carefully with a measured amount of the EDTA solution. So EDTA forms stable complexes with the calcium and the magnesium ions in the water, effectively chelating them. So we are using the indicator Eriochrome black tea EBT indicator. It is to determine the endpoint of the titration, which changes the color as calcium and the magnesium ions are completely complexed by the EDTA. So this is the structure of the EDTA and this is the Eriochrome black tea. So the determination of hardness with EDTA. So in this slide we can see that the calcium, it forms complexes with the EBT, calcium EBT complex, which is an unstable complex and it has a color, that is wine red color. What is the color of EBT? The EBT color is blue. Free EBT color is blue, but when it's complex with the calcium or magnesium ions, it forms wine red color. So calcium and EBT will be in the solution. When you add EDTA to it, the calcium starts complexing with EDTA. Okay, but why it is complexing with EDTA? Because complex with the EBT is an unstable one, but complexing with the EDTA is a stable complex and it is colorless. Plus you have the EBT, that is a free EBT, which is blue in color. So this titration is also called as complexometric titration because you are doing the titration in which a complex formation is involved. So same reaction occurs in the case of magnesium also. So at the end of the titration, EBT is released free, resulting in the formation of blue color. So the first step is the calcium ion coordinates with the indicator, that is areochrome black tea. And the second step, the EDTA chelates the calcium ion and releases the indicator. So you have a color change from the pink or wine red to blue. So EDTA, it binds to calcium ion by forming 4 special covalent bonds called the coordinate covalent bonds. In today's experiment, in this you will go to determine the total concentration of calcium and the magnesium ion in hard water sample using EDTA in a solution buffered to a pH of 10.